Geography at Ohio State University. And his research interests are in mobility, accessibility, and social equity, enabled by new forms of high resolution transportation data, and also his own personal experience being a non-driver in an American city. He has his undergraduate degrees in mathematical sciences and urban and environmental science from Peking University. He did a master's here at Ohio State, and now he's working on his PhD. Along the way, he has earned a graduate certificate in college and university teaching. He's actually had some teaching experience teaching fundamentals of GIS and also some visualization workshops for the UCGIS and some other venues. He has a bunch of project experience. He was a Cura GRA, and he's worked on a couple of high visibility projects, in particular the MORPC Sustainability Agenda Dashboard, which won an award in 2020 as part of the team effort. So good work on that. And let's see, he has publications in some really nice journals: Urban Studies, Transportation Research Part A, +1, and International Journal of Geographical Information Science. And today he's going to talk about, I believe it is reevaluating public transit. Take it away, Luyu, please.
Okay, thank you. All right. Okay, I'm making sure we're recording, right? We're recording. Great. So welcome everyone to my talk. So we noticed that there was a little bit of adjustment on my title here, which is okay. So the point is I want to focus on two things today, which is public transit plus accessibility. So again, my name is Luyu. I'm from the same department as yours. And thank you for coming. So before we jump into the topic, I want to talk about what is accessibility, right? Accessibility, we can just break it down. When I was teaching, I love to break things down. So accessibility is like access plus abilities, right? Basically, it's literally just your ability to access some things. And some things can be some places, for example, how far you can go in 30 minutes, right? If you, it's like competitions for everyone. If you can go further and access more places, you naturally get more opportunities. For example, like the primary concerns for us usually is jobs, healthcare, right? If you have more jobs accessible in, let's say, 15 minutes, it's better for you, right? You get more competitive and you better probably get more opportunities than other ones. So again, there was a famous quote from our domains that says accessibility is literally your freedom to move, right? Which again, public transit usually lacks. Like, let's just look again at the public transit, right? So public transit, like literally is public transit, right? Public transportations. It is a more of a collective way to help you move. But meanwhile, it is also a kind of your compromise to some certain of a time schedules. So basically you cannot just tell and the bus driver to, okay, I want to go to that place. It doesn't work that way. So you have to compromise your own schedule with everybody else's schedules. So that's how public transit works. But meanwhile, that makes the accessibility smaller than like say vehicle, because you have to you cannot just directly go there, right? So that's why we care about these issues. But meanwhile, we can see that public transit is definitely not doing well in the US. And that's why the question we want to ask is, why do we fail transit accessibility? Why people cannot go as far as we think we can go? There was the three major problems I want to talk about today, but of course it does not cover every perspective. It's this such a huge questions. But first one, I think, the reason we do not understand well why we do not have the very strong accessibility for public transit is that we do not actually measure it well. In fact, we cannot know exactly what people are experiencing from the data we have right now. So traditional studies use a schedule data. So we all know schedule data as in like the timetable on the walls, right? Like old times. Like timetables we'll see enter the train station, for example. So we have similar things for the buses, but it may be just not on theirs, but you can definitely assess that by your cell phones or some website. But the idea is that the schedule data is not reality. There is so many variations that happenings can make the on-time performance difference from what transit authority expect. And therefore there could be delays and early arrivals, and that happens a lot. If you use transit system, you will notice that there were so many delays, so many early arrivals can actually make this whole on-time performance totally not reliable for you. The second question, I think, is the transit is dependent on other modes. In fact, no transportation modes is on its own, right? Even if you want to drive vehicles, sure, you can drive whenever you want, but guess what? You have to walk to your cars and drive, and therefore after the drive, you have to take off your bus, take off your cars at the parking lot and walk to the place that you want to go, right? If there was a parking lot a mile away, you still have to walk. The same things happen for the public transit, but the thing is, it is more severe and more obvious for public transit because, as I talked before, it's a collective way for us to move. So you have to compromise your own schedules. So sometimes you may have to walk very long before and after taking the bus. So that's why we call this first mile and the last mile problems. And sometimes this is so long that sometimes it can be the bottlenecks of the entire trip, which make it harder for people to use this transit system actually. So that's why we see there were so many solutions like bikings and the scooters, which is the topic I want to talk about today. And then there was another issue, major issues for the failure of a transit accessibility, which is the accessibility is a super heterogeneous experience. Like we, as non-disabled person, we can walk as far as we like, but guess what? If you are wheelchair users, that thing could be super hard for you to pull off, right? And the whole fixed route transit is super disadvantageous towards people with mobility disabilities. But meanwhile, there was an act back in the 1990s, the American with a Disabilities Act could guarantee so-called equal opportunities for disabled passengers. So my question here is that true right now? Is that really the case for the disabled persons, right? So here comes the three papers or three research questions I want to talk about today. So what is the realizability and the reliability of our current transit accessibilities? And second is that what is the micromobility, which is the new emerging transportation's impact on the current public transit accessibilities? And the last is how about the people with wheelchairs? What do they experience as participants in these transit systems? So with these agendas, first the paper we want to talk about is called the realizable accessibilities. Like I said, schedule data is not real. It's so unreliable that sometimes you just cannot trust that. But guess what? It is static. It is very available. It is like the expectations from the authorities that give you some ideas about how the system works. But however, due to delays, the traffic, and weather, like today, we have so many sleetings and the snowings. Sometimes it can make the whole systems performs like less ideally than usual, which is what is the ideal scenario is. And real-time data is more reliable, and it's a much, I would say, it's represent what it actually is experience, because when you want to use the systems, actual arrival times is the ones you actually experience. You have nothing to concerns about the schedule, because that's like the fake things that that authorities think they are going to make it work, but reality is a lot of times they won't. So why don't we just measure with actual times, right? Why don't we just change the schedule time to the real-time times, which is the change the numbers, right? And I'm not going to dig into these issues, but we have so many well-established models that we can just use that, right? Isn't that super convenient? Well, yes, people actually did, right? These people from University of Toronto actually did this, they retrospectively calculate the real-time accessibilities. So by retrospectively, they mean that they kind of like a scientist that collect all the historical actual arrival times and calculate everything that happens in the past. It's like they are kind of like the people from the futures that know all about the past and they calculate everything about accessibility about the past. So they find that by this, they kind of find out that the retrospective real-time accessibility is significantly different from the scheduled accessibilities. And yeah, that's basically the conclusion. Basically, this actually can prove that scheduled accessibility is not reliable. But is that the end of the discussions? Well, of course not, right? My questions for this question is retrospective real-time accessibility even realistic? So it's like the double questions, right? Well, the short answer for this is no, because if you do the so-called retrospective, basically you are the scientists from the future and you collect everything from the future about the past. Basically, you assume cleverness or perfect perfect real-time informations. The fact that there is no one can tell buses of actual arrival time before taking bus. And sometimes if you calculate everything from futures, you can actually think you can pull off some maneuvers that theoretically is possible, but some normal passengers just cannot foresee it. I would make this metaphor that, it's just like buying a lottery when you already know numbers, right? Well, you can say, I have this number, why just you can buy the right tickets, right? Why just can't be rich? Why don't we just start world peace, right? It's exactly like that. You just don't have the knowledge in the past, so you just can't do that physically. And meanwhile, what a plan can be different from your take. Basically, what if I want to do something, and what if I follow these plans and do this in the realities? Can we actually do that? A lot of times we can't. That's how life is, right? But meanwhile, if you do those things retrospectively, you basically achieve whatever you like. So I will give you some example. For example, let's say we're taking a transfers, right? So this is exactly the same transfers. So we have the bus, we're in this yellow bus, and we want to take transfer to the second bus. So if you're a scientist who has full knowledge with full archive of the historical real-time data, you basically already did this, right? You can imagine you are like the godlike figures from the futures, already experienced all these events that happened in the past. And then you just go back to the past and just want to re-simulate everything. And basically you can predict the bus will be delayed for 2 minutes. So therefore, just enough for me to catch it. So this transfer is possible. Well, of course you can do that because you know this bus will be delayed. But what if you are just the normal persons who can just only assess scheduled data and the current real-time data, right? And based on your current knowledge, you can never know this is a possible event. Or even if you know there is a slim chance that the bus may be delayed, you wouldn't do that, isn't it? And so that's the very point of this why using a new set of accessibility measures is very important, because it is actually realizable, it's doable. If you want to do this in the actual world, it can be done, right? So that's why we introduce realizable accessibilities. It is a two-step behavior process. The first step is plan with scheduled data, because scheduled data is available in the world, and you can, although we can say it is not reliable, but it is the only things we have if we cannot predict the future, which we can't, right? And the scheduled data is the only thing that we can assess beforehand that events actually happens. And then with these plans, we can implement with the actual times, and we can, so basically it's like that we have the hypothesize users, which just tell the person to plan according to the information they had, and they ask them to propagate their areas of the map. Well, to the right, I show the map of the different scenarios. So we have the scheduled scenarios, where basically is the ideal scenarios from the transit authorities. We have the retrospective, which is the future God figure scenarios. where you can predict the futures, and the realizable ones, which is the orange ones, you will notice that it is the most conservative one. It is, I would say, it won't actually overestimate your ability to go into the space and use the transit systems. And it's actually the smallest ones, which is a good thing because this is what you can do. This is what you actually can pull off. And how unreliable is public transit, right? So we want to define this unreliability because from the, so to the right, I showed an example of how far you can go from the center of the Columbus downtown in the real world, which is in the orange colors, versus in the schedule, which is the blue. Now you will notice that this orange one is always smaller than the blue one because that's basically how the world works, because you cannot see what's going on right now. So you have to make your performance cannot be as ideal as we expected. So I would say it's kind of like a degree of a broken promise. The promise is like the schedule the transit authority gave you, and they guarantee that it will say to you that, okay, I guarantee this system will work well, at least as close as the one I promised. But in fact, if you actually use that, the performance will be different. So we want to calculate the difference between these two stages, and we call it unreliabilities, right? So after we know these measures, we want to see how that change over space and times. And here we show animations of the unreliabilities patterns. So we have a time budget, basically how far you can go in the space. Now notice that this is not just the one people's. This is one people that we ask this person to go in the space. But you know, it is just the one place. So we ask everywhere, every bus stops in the city. This is like a 3,000 people in the maps, and we ask them to simultaneously do the same things as the things we ask them to do, like propagate and compare the performance in the ideal scenario versus the reality scenarios. And we calculate the difference between the two scenarios, and we visualize with a color. So the red colors means that there is more reliability, and the blue colors means there is less reliability, unreliabilities. So we can see here as the time budget from the very few, basically 5 minutes to half an hours, the centers will be actually more unreliable, whereas more services is at, which is actually making sense because more service at, more opportunities you add, actually more chances you will miss a bus. And as your times gradually increase, you actually spread out to the whole cities and outer rings of the cities. So that can give you some ideas of how the system works. And this is actually a very, also the kind of word for me to say, this is actually very powerful visualizations that we can actually see what's going on in the system, right? So with this conclusion, we can, I have 3 conclusions. The first is that we often overestimate the abilities of user to use transit systems. And that is something I think it is the most, how to say, a very, very sad things to have. Because, you know, you basically just expect a very high standard for the user, and the user just cannot pull it off, right? And the second, we should be more conservative when planning transit systems, is that, you know, we cannot expect user to do the maneuvers like 3 transfers in 2 hours. That's impossible, right? We should be more, making more humane in a way that, you know, actually human can actually do this. And the last is that transit system should be more about humans, less about the system. Although we still do all the measurements about the systems, but still we want to make the simulation more about human, less about the buses, right? We care about the humans. We know that it is the human user system, not the buses, right? So that's the first part. I'm going to change to the second part. So like in the very beginnings, I talk about, you know, first mile and the last miles, right? The first mile is like before you're taking a bus, and the last mile is just after you get a bus, you want to go to the destinations. But sometimes people just find out walking is so awesome, it's not very attractive walking is so troublesome. So there was a new transportation modes called micro mobilities, or sometimes people call it chocolate scooters. It is a very flexible and a fast alternative to walking. Basically, it's everywhere, right? If you're in the right neighborhoods, of course, and it can be very fast to unlock. It basically don't have to like manually just like lock it or ask someone to lock it for you, right? And it is very faster. That it's relatively faster than walking, right? Walking is like relatively slow, but if you take a scooter, it can take you further and take you faster. And it can help solve so-called the first mile and last mile problems. If you do not want to or feel like walking, you can just take a scooters, right? Theoretically, well, it can maybe be a efficient problem solvers, right? Or is it? That's the question I want to ask. So with these new systems, I want to ask, what is the impact on the current public transit accessibility? We know that accessibilities can actually impact the qualities of your experience when taking the public transit, right? So after you introduce such a new system into these in the urban areas, what if people want to use these two things together, right? So this is why this problem comes into my my visions. Well, first, let's just talk about the last miles. What is the impact on the last mile? Because first mile, last mile, they are different things, although we just tend to just merge them together. But no, let's talk about the first last miles first. So last mile is after you exit the bus. Now here I show the visualization here. So after you take a bus, you can actually have two choices. If you do not choose to take a scooters, you can just directly walk to your destinations. Let's say your homes, right? Or you can take a different route to a different scooters and take a scooter to your destinations. And it is very, I would say, if you choose the right locations, choose the right scooters, you will actually save more times. And scooter help you move faster and further. It can help you save times. It can even help sometimes save buzzing time by skipping some transfers, which I will talk later. And the last miles, since it's the last leg, literally the last leg of this whole trip, it can be linear, which means there is no tricky things. It's just if you save times, that's the time you saved, right? There's no way you can change that. This basically is very simplistic natures of this process. I say this linear because the first miles is more complicated because first mile is before you boarding the bus. So like the last mile, scooter can also help you move faster and further, but the difference is that there is more trips after you take that scooters. So basically you can use a scooter the same, even a small save amount of times in the first mile, but that save time can actually save a lot of time later for the whole trips. I can give you an example here. So this is one of those examples that you can save by skipping a trips. So if you do not have a scooters, this is the distance you have to walk. So you notice that you cannot access anywhere. You can just take 1, 2, 3. You have to take 3 buses, which is 2 transfers to the place. By the way, this is Eastern, where the shopping malls is that, right? But however, if you can take a scooter here, for example, you can actually walk and move further than like the traditional ones. And therefore, what you can do is that you can skip the whole transfers and take a different routes. I believe this is a 32 or 31s that directly take you to the Easterns. So that's why there's no transfers in these routes. And therefore, you can see this is saved actually almost 20 minutes. That's a large amount of times for a transfer. And based on these rations, we can actually see that accessibilities can actually improve accessibility of the public transit. To the right, I give you the same ideas, right? I ask a person standing here and ask the person how far you can go with and without the scooters in 30 minutes, right? I give you 30 minutes to go as far as you can and how far you can go, right? You can see there is actually difference, right? Without the scooters, there was like much smaller than with the scooters. So that's definitely tells there was definitely impact of the scooters on the public transit accessibilities. it can give you more accessible areas, more opportunities like jobs, healthcare, education, theoretically, right? If you choose to use them again. So that's why we want to measure that. So to measure the accessibility increment, basically how many times or how many opportunities you saved by the scooters, we measure by the travel times, because less travel times means more accessible a place, right? It's basically like an inverse relationship as the accessible areas, right? And accessibility increment is, we define it as the average save time due to scooters. So to the right, I show the accessibility increment in the first mile and the last miles at the stop. Basically, how many benefits you received as a bus stop from the scooter systems. As you can see, the most benefit concentrate on the city centers. And Ohio State is here, and the urban areas, like some urban areas, and the last mile is even more congregated. And meanwhile, notice that this legend, notice that how first mile is significantly larger than the last miles. So that says something about the so-called non-linearities, is that even if there were small save in the first miles, you can actually save a lot of times afterwards. So that's why the first mile is significantly larger than the last miles. And of course, as said, there was definitely some limitations, right? The first, as you can see, these two maps, you can already feel like, this is super unequals in a way that why there was only benefits inside these boundaries, right? Because that's where most of the scooters are, right? So like here, as I show another maps that shows additional accessible jobs due to scooters in 30 minutes. And you can see most of these opportunities are lying inside these boundaries where most of the scooters are. And honestly, these places where we are, and Shore North and downtown area, these places are very small areas and very privileged areas. So, and meanwhile, scooters are very expensive. And for this reason, I never use a scooter. Although I studied it, I use public transit a lot because it's free, because OSU give me pass, but I never use a scooter because it requires $1 to unlock and $32 per minute after. That's ridiculous. So that's why I do this analysis, and to see how many money you pay versus how many money, how many increment or benefits you can receive from the scooters. You can see here where most, let's focus on the first small increment, where the most, which is the most main source of the increment. As you move towards the small amount of money you pay, the increment you get is rapidly decreasing. That says, if you do not have money, sorry about that, right? You're not getting a lot of opportunity benefits. And meanwhile, even if you pay more to the last miles, it will actually decrease, which means more money paid does not guarantee more increment in the last miles, because longer scooter trip does not actually give you more benefits. And the last limitation is limited capacity. We all know scooter is not famous for its capacities. But meanwhile, public transit is very efficient at moving people, because one bus can carry 40 to 80 people. But scooters, you can only carry once, right? If you do not care about life, maybe two. There is more concrete users if there is scenarios where more users, let's say you want to hang out with your friends, right? Then you want to use the scooters, right? Guess what? If you do not have the equal amount of scooter available in your surrounding areas, you cannot use it, right? So that's why more concurrent users require more scooter available in your space. So that's why I do this analysis here to test how sensitive is the increment or the benefits that you receive from the scooter systems behave according to the number of people in your parties. And we observe that it will decrease rapidly. As more people trying to use scooters, the increment will rapidly decrease, especially in the early stage. So if you have two people, you basically just rapidly decrease. So that's the idea. So that's our conclusions. I have two major conclusions in these papers. Well, first is that the Dockley scooters have potential to remedy public transit's first mile and the last mile problem. Of course, we see that in the analysis that it can indeed expand accessibility areas and can shorten the travel time. However, these three factors can prevent scooters from collaborating with public transit. Well, the high cost, injustice of a spatial distribution, and the low capacity can make huge impact on the outcomes of its increment. So that really give you the more lessons for the future planning and the scooter vendors' policies. If the vendors cannot address these issues in the future, like planning or operations, they can hardly claim there is a benefits that's happening in the public transit systems. That's my argument. The last one is the mobility, disability, and the transit. So like I said in the beginnings, disabled persons is such a special group in the transit communities, you can call that. As they are moving much slower and much closer than a so-called non-disabled person, which is like the default expectation for the transit authority. So if you ask a transit planner to plan the systems, well, a non-disabled person is definitely like the primary target user groups, right? But meanwhile, we can see there is still requirement for disabled person. So when it comes to public transit, there is basically two options for the disabled person or people with mobility disability, because that's the this very special group inside these disabled persons. So there's the two options here. The first option is paratransit. You can see here I give you some example for the paratransit. So paratransit is basically like a minivans that operated by local public transit authorities, guaranteed by the American of the Disability Act of the 1990s that guaranteed the so-called equality, equal opportunities, right? So it's on demand. Basically, after you board after they board you, if you are disabled persons, after they board you, you can tell the bus driver just go the place I want to go, right? But guess what? Because it's on demand, you cannot actually just do that every time you wanted to do, right? So that's the reason a lot of people actually still need to rely on a fixed route transit. So it is so basically it's just like traditional transit, and you still need to walk or use a wheelchair outside the vehicle, which definitely will incur more difficulties. And sometimes the people with the mobility disability still need to rely on a fixed route transit. And meanwhile, as I said before, that they are very disadvantageous because they have a lower speed and a shorter reachable distance. Now, this is the case in the realities. So here's I show the maps that shows. So basically, again, do the same simulations. If you start on here as a non-disabled person versus a disabled person, we have two persons standing in the same place, and we ask them to go. Let's say this is 30 minutes to go the same amount of times and how far you can reach. And this is a difference. You can see the disparity is so obvious. The red areas represent the disabled person's reachable area, which is much smaller than the ones for the non-disabled person. And also remember that they are taking the exactly same systems. Although they are taking the exact same locations, exactly same buses, they can be very different. And the passengers always assume to have the same accessibility in the planning stage. So basically, there is really no explicitly addressed issues that to guarantee that these two areas are less, less drastic, to say. So that's why I called it is very overestimated for wheelchair users. And meanwhile, we have some basic fact about three types of users that can make an impact on these issues. And remember that even if within these groups that people with mobility disability, they still have distinctions. For example, like many wheelchairs, they move much slower and much shorter than both of these later two, which is the electric wheelchairs and the non-disabled persons. So they can move faster, but the electric wheelchair is still much slower. And meanwhile, sidewalk can be a major factor. Now, sidewalk, although it can significantly impact transit accessibilities, it's not actually part of the transit systems, right? Now remember this, when we talk about planning, we have nothing, well, let's say it should be, of course, it should be part of the transit planning, but if you ask any transit authority, do you ever consider improving our local like sidewalk networks? I will guarantee that no one will answer yes, there was actually plan to address that problems. So despite not a part of the transit systems, there's a huge factors that it can impact your quality of your service. Now here's I show two examples here, right? That were corresponding to the two major problems in the sidewalk problems. Well, first is the surface conditions. If there is a bad surface conditions, it can make huge impact on how many places you can access. And here I show the manual wheelchairs, and the different types of wheelchairs can actually make a huge impact. And also, they also require different kind of like surfaces. If you can, for example, like these terrains can be barely passed by manual wheelchairs, but like power wheelchairs can probably just move faster. And meanwhile, connectivities. The question is there a sidewalk at all, right? For example, like here's a wheelchair user has to ride in the street with cars. That's so terrifying, isn't it? Even if we're bicycling with with all the cars, that's already very like scary for me. But if you imagine you're like in the wheelchairs and you're competing with cars, what kind of feeling is that, right? So that's why I do another simulations to investigate these factors. So we have the non-disabled versions of the white versus blues. You can see as you move from the linear distance, basically you can just walk from A directly to B without any network, just straight like from A to B, right? And then the blue one is using the actual sidewalk networks. If there is a sidewalk, you cannot go there, right? And therefore, we can see a huge difference. Like here's, there was a huge difference. And meanwhile, for disabled persons, there was definitely some difference. Like here's, the black one is the sidewalk, the Euclidean one is the red. You can see there were some places that after you consider sidewalk in the analysis and the simulations, you cannot no longer assess. So that's why sidewalk is such a huge factor in these problems. Both disabled and non-disabled persons are impacted by these factors. And we just keep talking about accessibility, right? Accessibility, like I said, is theoretically how far you can go, right? It's so-called the usability of transit. It's the potential and the supply of services, but it does not represent how people actually use the transit systems. So meanwhile, ridership is another story. Ridership is the actual usage of the transit. It's more or less like represent the demand of the systems and the demand of a service. It's kind of like a realities. So we want to analyze on the riderships to see how disabled persons actually use this, fixed route systems. And by the way, yes, there is a lot of people with disability using fixed route transit. I know a lot of you are already thinking, why should we care about this? Nobody uses that. Well, there's actually a lot of people using that. We can see later. Well, first, before we see the numbers, what we want to see about, what's the mechanisms behind these data, how to generate this, right? So CODA have this automatic passenger counter installed on every buses, and they can install on, no, not every bus, but most buses. They can they can detect the user's movement so that it can count how many people get on the bus, get off the bus, right? The same story with disabled persons. Only difference is that they count not people, but the ramp activations. Basically, every time, I guess many of you already see this, that when you see a wheelchair users want to get on the bus driver will press the buttons and the bus will and get off, and therefore there was a ramp activations that expand that the user to get on the bus more easily, right? So we basically count that movement, and the CODA staffs confirm that these measurements are 99% accurate, which is a good news, which means we can actually use this data and these measurements better to know about the statistic of the disabled person. And here was the result, right? There was so 145,000 activation of 16 million total riderships, which is almost 2%. You may not feel like 2% is a lot. This is actually a huge number. 2% is basically like every 50 person, there is one disabled person taking a bus. Imagine that, right? And this is from May 2018 to May 2019, so 1 year suspense. And of course, we will see different variation for different timelines, right? For example, after pandemic, how about that, right? So if we see, again, this is for the futures, we see some changes after pandemic, for example, the number rise or downs, we can see and interpret that result to see how the behavior of the disabled person's movement changes. And we can see here, this is a map here. We can see this is the high street. This is the main street where the number 10 is on. So number 1, number 2, number 10 are the busiest one in terms of disabled riderships. And very interestingly, we have another cluster here, like some places where we thought there should be less ridership, but yes, there's a lot of ridership here, and some cluster or outliners that is super interesting, that it could be some social inclusion happening in these places. But again, it could be a future questions. So this is a work in progress. I have future questions about these issues. So the first is what's the pattern of accessibility disparity between disabled and non-disabled person? So, and also how different sidewalk condition impacted disability. So although I already show you an example of compare the two scenarios, what I'm going to do next is that I want to compare different levels of sidewalk conditions. For example, like manual wheelchairs users versus power wheelchair versus non-disabled persons scenarios. We can tell the difference. We can see the stuff how different conditions of the sidewalk can actually impact the outcomes of accessibilities, right? And meanwhile, we talk about the usability versus usage, right? So how usability shapes the usage, right? Is there any connection between these two, right? And are there any social inclusion for the people? Like I said, from these graphs, we can actually see some outliners. So what's happening there, right? But this is the third paper. I'm going to summarize the 3 papers we talk about today. So the first is that we talk about realizabilities and reliability of the accessibilities and the usability of the transit. I argue that the usability of the public transit is super overestimated. We should be more conservative about the measuring and the planning. And the second, we talk about the impact of micro mobilities. They does help, but there is so many issues happening. Without addressing them, we cannot claim they're helping. And the last is that people with a mobility disability are especially vulnerable, and we need to talk about the disabilities between them and the non-disabled person, which is the main target of the planning, which if we do not talk about that, we cannot guarantee this is so-called equal opportunities, right? For the futures, I want to ask more questions like the real-time information and impact on accessibilities and how to conduct evidence-based. We talk about more conservative plannings, right? How that can happen, right? How to do that exactly. And meanwhile, I want to know more about refined analysis on accessibilities. It's not just about the whole pictures. I do not want to see a more homogeneous patterns in the whole areas. I just want to see how about one people, how about one line, how about one stops. That can be much more refined and more meaningful for local scale. So this is all. thank you for your patience and any questions so far? I can answer that.
We don't have time for questions. I'm sorry, we're out of time.
Okay.
So I'm gonna turn it over to the next introducer.
Thank you, Harvey. Hi, it's my great pleasure to introduce our next speaker, Jian Wang. Jian is currently a third-year PhD student in the Department of Geography, and he received his bachelor's degree in remote sensing from Wuhan University in 2015, and he continued obtaining his master's degree from Chinese Academy of Science in 2019. And Jian's research focused on remote sensing of plant phenology, terrestrial ecosystem carbon dynamics, also land use, land cover change, vegetation dynamics. He also studied the permafrost soil using remote sensing and ecosystem modeling. And Jian received a number of honors and awards, including the most recent one, the OSU Presidential Fellowship. And he has published 15 peer-reviewed papers, including one in Nature Climate Change, which is actually today's topic. He's going to present that paper. He also published another paper in PNAS, Proceedings of National Academy of Science of the United States of America. With that, I want to turn to Jian. Jian, please.
Okay. Okay, hi guys. Can you hear me?
Yes.
Okay. Hi guys, I'm Jian. Thanks to my advisor for introducing me. I'm happy to be here giving a presentation of my recent work. Any questions, suggestions, and comments, welcome. And my research title here is Decreasing Rainfall Frequency Contributes to Earlier Leaf Onset in Northern Ecosystems. First, I'd like to give a brief introduction of the concept or definition of plant phenology. Plant phenology investigates the seasonal changes of characteristics of growing up, flowering, and leaf coloration, and their interactions with interannual variability of climate change. And many studies have demonstrated that plant phenology is a sensitive indicator of climate change, and it has been extensively used in ecosystem models. The upright figure here is from a review about the plant phenology. And we can see the climate change can directly impact the plant phenology, and phenology can regulate vegetation growth and activities, further feeding back to the climate system. So plant phenology is a science that studies the patterns of vegetation periodic growth and its interaction with climate change. There's a paper published on Science said that the phenology accounts for 1 out of 8 biological processes influenced by global change. Also, IPCC reports that the plant phenology is one of the key indicators of ecosystem response to climate change. So we can say phenology research is important, not only for plant itself, but also its role in climate change. Here we move to the previous main achievements on plant phenology research. First, we talk about the observation methods. Actually, the concept of phenology has been mentioned in some ancient poetry in China. And then in the modern philology times, there are more and more phenological networks built for scientific research. With the emergence and the development of remote sensing technique, we stepped into the global climate change phenology times. So now we can apply many different tools and techniques to monitor the plant phenology. My research focuses on the spring phenology, or we call it leaf onset date, LOD. One of the major findings of the LOD is that LOD has been advancing during the last several decades. For a review published in 2019, we can see first the bottom three figures here show the temporal trends of in situ LOD in Europe, China, and the US. Overall, all this evidence confirm the advancing trend of LOD. From these three figures, we can see the red color is advancing part. The upper right figure gives the temporal trends of LOD derived from satellite greening product. It also shows the advancing trend in middle to high northern ecosystems. So now we know LOD is becoming earlier and earlier. So what's the drivers of advancing trend of LOD? First, temperature could be the main forcing. Air temperature triggers leaf onset, and the daytime temperature controls the leaf onset. From the right figure here, we can see the temperature sensitivity of LOD is overall negative, which means increased temperature will lead to earlier LOD. Also, a recent paper said like urban warming can also advance LOD. So apart from temperature, some other factors have been studied, such as photoperiod, which is related to solar radiation, and soil nutrition and water availability. Few studies also reported the precipitation, and they said like winter precipitation amount can impact heat requirement for leaf onset, but precipitation related research is still limited. So now we know LOD is becoming earlier and earlier on the climate change. From a broad view, what's the implications for future phenology study? On the basis of IPCC report, there are three important scientific problems. First is phenological simulation accuracy is low. Then the mechanism of climate impact is unclear. And the last is the connection with carbon cycle is weak. So more efforts are needed for these problems. Taking Tibetan plateau regions as an example, there are totally 8 papers published on PNAS about the debate on the spring phenology in the last 10 years, about whether spring phenology is advancing and what the drivers and how it responds to the ecosystem productivity. So given most current studies still focus on temperature, this research tries to investigate the impact of precipitation on LOD. We have 3 scientific questions. The first is how to better understand the effects of the precipitation on spring phenology. Is there any other characteristics of precipitation besides precipitation amount? The second question is what's the mechanism on that precipitation controls LOD? And the last is about the application part, is how to improve the modeling and projections of LOD by incorporating precipitation information. For this part, we used the 4 independent datasets to extract LOD in the study area, including long-term ground phenological records in Europe, China, and the US, and we call it ground-based LOD. We also use the eddy coverance-based flux measurement. We use the gross primary productivity to determine the GPP-based LOD. And we also used 2 satellite-based NDVI products from Mobilities and Jian. We used different methods to extract the LOD. To save time, I'm not giving too many details here. The right figure is the distribution of the in-situ, the right figure here is the distribution of in-situ and flux tower size. And then for these 4 different independent LOD, we calculate the temporal trends of LOD. From this figure, we can see LOD at different scales, like FluxNet is from the eddy coverance flux tower and in-situ observations and satellite observations. All these LOD showed advancing trend. Here is the blue color shows the negative trend, which is the advancing trend for ALD. We can see the negative trend is dominant. So this result is consistent with previous findings that ALD is becoming earlier and earlier. We also used many climatic data in this research. For example, we derived monthly temperature and cloudiness from CRU, and also we derived a monthly precipitation amount, precipitation frequency from CRU and AGEI5. From the right figure, we can see for spring season, precipitation frequency from CRU and AGEI5 showed similar temporal and spatial patterns. And from subfigure A and B, the negative, which is the blue color, is much higher than the yellow color, which is the positive trend. So we can see there are a lot of areas experiencing the decrease of precipitation frequency over the northern ecosystem. We also use daily temperature and precipitation for LED modeling and projection. Some other data we used here include runoff data, a drought index called SPI, and volumetric soil water. For analysis, we use a TS slope estimator with MK test to determine the temporal trends of ALOD and precipitation frequency. In this study, we frequently use the partial correlation analysis. The reason we use partial correlation analysis is that many factors can jointly and interactively control ALOD. We use the rigid regression to estimate ALOD sensitivities. For modeling part, we built a new model called weighted precipitation growing degree day, and compared with two widely used models, which is conventional threshold and GGD model. The details will be given in the following slides. As to the variations of precipitation frequency, we found widespread decreases in northern ecosystems in winter and in spring, from graded, which is subfigure A, B, and D, and also from FluxNet, which is rain gauge data. We can see from A and C. Spatially speaking, decreasing trend of precipitation frequency were widespread, such as in Siberia and also Northern Europe. This decreasing trend is consistent with previous observations and model projections. Two potential reasons can explain this decreasing trend. The first is the surface warming or thermodynamic contribution. The second is weakening of tropical circulation or dynamic contribution. So to investigate the response of ALOD to precipitation, we first need to remove the impact from other factors. So here we use partial correlation analysis for three scenarios. The first scenario is precipitation amount versus ALOD controlling the effect of temperature and cloudiness. Then based on the first scenario, the second scenario is adding precipitation frequency into the controlled list. The last scenario here is the precipitation frequency versus ALOD controlling other three factors. By doing so, we can understand the role of precipitation frequency in the precipitation ALOD relationship and its impact on ALOD. So here are the results of partial correlation analysis on the three scenarios. Overall, the analysis confirmed an essential role of precipitation frequency in controlling the effect of precipitation on ALUD. Because when we compare the figures in top two rows, we can see the first row is scenario 1 and the second row is scenario 2. We can see after controlling the effect of precipitation frequency, the percentage of significant correlations dramatically decreased. And then for scenario 1 and scenario 3, both scenarios showed positive dominant correlations, which means with a decrease of precipitation frequency, the LED will advance. And grouping the correlations into vegetation or species types, we can see the woody species or forest is positive dominant, while in the green box you can see here is the herbaceous species or grassland is negative dominant. This is also like the TG and MG here is grassland for the satellite observation. We can see the blue part is negative correlation and the red color is positive correlation. Only these two vegetation types show like the opposite trend of this like percentage of the partial correlation distribution. So these opposite patterns will be discussed in the following part. We also used soil moisture and soil temperature to classify partial correlations. From the heat map here, we can see partial correlation coefficient showed clustering patterns with some signs. Overall, negative correlations were generally located in some warm, like you can see the right side for the green line. It's warm, and also for this part is the negative part is focused on the dry regions. So some warm and dry regions is like negative dominant. We may ask that whether the rainfall size matters. So here we calculate the partial correlation coefficients using precipitation frequency at different levels. We found that 2/3 of the significant correlations between precipitation frequency at 1 millimeter per day and LOD were positive. However, this positive dominance became non-existent for the precipitation frequency at 5 and 10 millimeters per day. This result suggests that the effect of precipitation frequency on LOD is controlled by the total precipitation frequency instead of the frequency of some large rainfall events. So here we try to quantify the precipitation frequency effect using sensitive analysis. To be noted, the absolute value of sensitivity is defined as the climatic signal. And when one climate signal is higher than the sum of other 3 climate signals, we define as the dominant factor that controls LOD. So based on the GEMS NDVI for this figure, we found that the precipitation frequency dominated nearly 10% of the area, suggests an important role of precipitation frequency in explaining LOD variations. Overall, temperature has a negative dominance from the subfigure C. We can see the temperature has a negative dominant effects on LOD, while precipitation frequency, which is D, here is the positive dominant, especially in some high latitude regions. In addition, based on the spatial average sensitivity, we can see the precipitation frequency has a stronger effect on LOD than precipitation amount and cloudiness. From the mean value here, we can see like the stronger effect from precipitation frequency. So all these results suggest a positive contribution of precipitation frequency variations to the advance of LOD. So the left figure here is the sensitivity analysis for MODIS NDVI, which is show the similar results for with the previous slide. And the right figure is for ground-based LOD, which is also consistent with the satellite observations. Interestingly, when we check the sensitivity of the precipitation frequency, you can see the green box here, and we can see the opposite distribution for the woody and herbaceous species. This is consistent with the previous partial correlation analysis result. So to explore the effect of precipitation frequency on the precipitation amount sensitivity, we also compare the signal of precipitation amount in springs with high and low frequency. From both ground and satellite observations, we find that the signal of precipitation amount for springs with low frequency is significantly higher than the springs with high frequency. So the difference of the signal here is positive dominant. This results indicate the nonlinear response to the precipitation controlled by the frequency of precipitation. So from previous analysis, we know that the effect of precipitation frequency is positive dominant, which means like the decrease of precipitation frequency will lead to the advance of LOD. The positive correlations were mainly for woody species and located in some cold and wet regions. However, the effect could also be negative, especially for herbaceous species in some warm and dry regions. Here means like with a decrease in precipitation frequency, LOD would delay. But what's the mechanism? So we move to the mechanism part. For the positive effects, it can be described as the decrease in precipitation frequency positively contributes to the advance of LOD. So first, we focus on the radiation. Surface absorbed radiation is directly influenced by the precipitation frequency, supported by the negative partial correlations between the flux tower based precipitation frequency and radiation annual variations. This figure shows the negative correlation between precipitation frequency and radiation. And also graded analysis, which is a subfigure A, which is also supports this negative relationship. And we move to the radiation and the LOD. We can see nearly 75% of areas with a significant partial correlation, which is subfigure D, between radiation and LOD had a negative value, indicating that the decrease in the precipitation frequency associated with less cloudiness enhanced radiation and then lead to earlier LOD. We also focus on the daytime and nighttime temperature because the reduced rainfall frequency with more clear sky days and nights increase the daytime surface solar heating and decrease the nighttime downward long-wave radiation, leading to higher daytime temperature and a lower nighttime temperature. This contrasting effects contributes to the earlier LOD with negative, which is a subfigure E, and positive, which is a subfigure F, dominant partial correlations. So overall, we can say the decrease of precipitation frequency influence or related to the radiation and daytime and nighttime temperature, and then jointly control the advanced LOD variations. So here is the explanation of the negative correlation. Almost 1/3 of significant correlation between precipitation frequency and LOD was negative. So which means like with a decreased precipitation frequency comes with a delayed LOD, requiring like alternative explanations. Here we give a potential mechanism of the precipitation frequency effects on the grassland. Grassland here mainly focus on located in like semi-arid regions. So using reanalysis-based soil moisture and a drought indicator, which is SPI, we found that after removing the effect of precipitation amount, the decrease in precipitation frequency leads to lower soil water availability, which is subfigure A and C. And then the concentrated rainfall enhanced the water losses from runoff, which is subfigure B. This drought stress further delayed LOD as shown by the predominantly negative correlation in the subfigure D. So these results indicate that the decrease of precipitation could aggravate drought stress and delay LOD accordingly in grassland. And this tendency to postpone LOD and associated evapotranspiration could reflect a strategy for herbaceous species to adapt to the water depletion. Then we move to the application part. In this section, we try to improve the current LOD models and generate the projections of LOD. Current empirical LOD models are driven by daily temperature. The first one is called a conventional threshold model, or CT. And this model is pretty simple. The LED is defined as the day with higher temperature than the threshold temperature for 5 consecutive days. The threshold usually is 5, 10, or 0 degrees for different regions. And this model has been used in some process-based ecosystem models. The second model is growing degree days model, or GDD. GDD is the most popular and reliable LED model currently. Given our research has proved that the precipitation frequency contributes to LED advance, we think that temperature is not enough to capture the variations of LED. So we proposed a precipitation weighted GDD model here. We first determine the multi-year average intensity of precipitation for each pixel or site. Then we incorporate this index and the daily precipitation amount into the GDD model with a dynamic weighted factor. So to evaluate and compare 3 models, we use in situ and satellite-based LED as truth data. The criteria of the model evaluation includes the frequency of size of pixels with significant correlations, average R value, and average RMSE and ARC. From the bottom figure here, we can see, comparing to CT and GDD model, our new model has higher frequency of the significant correlations, higher average R value, and a lower RMSE and a lower ARCC. To be noted, a lower ARCC indicates a better trade-off between the predictive accuracy and the simplicity of the model, because we incorporate new variables into the model. So we use this variable to evaluate. We also compare the difference of the temporal trends for 3 models. Overall, we can see comparing to CT and the GDD model, and our model has a lower difference of the temporal trends, suggesting a stronger ability to predict the temporal trends of ALD. So this evaluation work confirmed the improvement of our model. So we move forward to applying this model to predict future ALD. We first use 3 models, CT, GDD, and GDD preg, to predict future ALD on the scenario RCP 4.5 and RCP 8.5. Then we determine the difference of our model and the current models, CT and GDD. We find that our model projected an earlier ALD than currently expected. And grouping these results into the vegetation types generates a similar results. And the data we used here is the ensemble mean, temperature, and the precipitation. So we also calculate the difference for each model in the ensemble to check the difference. And we got the similar results of the overestimation of ALD. Since we projected an earlier ALD than the currently expected, we can say that the length of future growing seasons and the amount of carbon uptake by plants might be consequently underestimated. We also predicted the trend of ALD of this century using the improved model. We found that the ALD will advance nearly twice as fast on the RCP 8.5 than the RCP 4.5. So this is a take-home message. And basically, our research found that the precipitation frequency is an important but neglected factor controlling the plant spring phenology. And the widespread decrease in precipitation frequency positively contributed to the advance of spring phenology. And also, solar radiation, daytime and nighttime temperature, and soil water availability can link the relationship between precipitation frequency and ALD. For the application, temperature is not enough to capture and predict the variability of ALD. Precipitation does help. So current model overestimates ALD. This is a data availability for this research, and this is a reference for this presentation. That's it. Thank you.
Thank you, Jian. Great presentation. And I think we have about 14 minutes for questions, and based on the guidance from GSC, we're going to give students priority. So any students questions for Jian? Or we can open to everybody if no questions from students. Anyone, if you have any question or comments, feel free. Or if you want to have some clarification, like want to see some slides. Okay, looks like everybody is looking forward to the Friday. You know, the weekend is ahead of us, and especially during the snow emergency today. So if no questions from the audience, then I'll take this opportunity to thank you everyone for coming to the colloquium, and wish everyone a great weekend. Intra, do you want to say anything to conclude today's colloquium, or we can just let everybody?
No, I guess we're done. So I have a lot of noise here, so I cannot. I can only unmute for 1 second. Yeah, good job, guys.
Okay. Thank you, everyone.